to the second session. Today we are talking about competing architectures to the conventional or traditional CPU architectures. Vishwesh went over GPUs as a challenge to CPUs, and now I want to go into FPGAs and kind of encourage you to think outside the box and kind of think of disruptive architectural technologies that can help accelerate applications, help look at energy efficiency, and come up with newer microarchitectures that could challenge the traditional computing world. So in this context, FPGAs are another fundamentally different architecture. And why are we looking at it? You might have seen this plot many times over the last week. We have the advantage today of many transistors being packed onto a single chip, and that trend has been going on and is being supported through various technologies, etc., advancements, etc. And we are seeing increase in transistor densities. The question is, are we making use of the transistors that are all available on a single chip? Right? So this is just a plot of time on the x-axis and transistor count on the y-axis, and we have reached phenomenal number of transistor counts on a single chip. The question is, how is this advancement being put to use? So if I were to put if I were to put this in another graph and say it's the exact same x-axis, and on the y-axis also it's the same thing. But now what I have done is I have extrapolated the numbers. Sorry, is there a question?
Sorry, ma'am. No, ma'am.
Right, so if I extrapolate the same thing, what I had in the previous graph is the number of transistors, which is still here. That has increased over time. And as a consequence, we are able to build really complex processors. This is a many core processor, let's say a 48 core Intel. This is a few years old, but we have many more such processors that have come along because of the transistor densities. GPUs also have come in the way because of transistor densities. But what has happened as a counter effect? Are we seeing, what do we expect? Now, just a question to the audience. If we have so many transistors being packed on a single chip, what do we expect out of it?
The computing power increases, but along with that, we'll also have a lot more power distribution into the flash area.
We'll have a lot more. Could you repeat that? I couldn't hear you well.
Because we put in pack in more transistors, it will have a lot more area, so they might have more power distribution.
Okay, so even if the area is the same, we are able to put in many more transistors, right? The same chip area, we are able to double the number of transistors every 18 months. So the area is the same, but the number of transistors are higher. But you're right, yeah, power increases because you have so many transistors which are going on and off. So power consumption has increased. That's a side effect. But what is our primary expectation when we say we have double the number of transistors available on the chip? What is our basic? Yeah, go ahead.
Double the number of transistors means we can pack more number of gates inside the processor. So be it in the form of adders or anything, the arithmetic units.
Yeah.
Increasing clock frequency.
Our capacity to be able to perform operations should keep increasing.
Yes, I think that is the primary requirement, performance, right? When we say I have 20,000 transistors last year, but this time I have 40,000 transistors. I mean, primary requirement or primary, how do I put it? I mean, a very basic understanding is that I expect it to perform at least 2 times better, right? Otherwise, why would I put so many more transistors? If more transistors is more cost, I know it is more power consumption. And even after paying all of this, if I don't get performance, then what is the point in putting so many transistors? So the question is, does performance transistor densities translate to performance, right? So let's take a look at this graph closely. This is the plot for the transistors. It has been growing steadily. As a consequence, we are able to pack more number of cores. Maybe it was the cores became complex, so it was single core, but then yeah, we put in few more cores. But the number of cores should have actually gone alongside the transistor slope, right? We should have had the same kind of slope, which we are not seeing. What else? Power consumption has a limitation. We cannot scale power consumption or power dissipation just as much as we scale transistors, right? Then you see these videos that say you can actually have fry an egg on your CPU chip, right? So power consumption, there is a limitation on how far we can do. What happens to frequency? Frequency is not going up the same way the transistor count is going up. You see that? The slope is not the same. It is somewhere flattening. So we are not able to scale performance in terms of frequency as the densities of the transistors. What does it mean? It translates to performance where it is flattening. What we would have expected is this orange line where if we pack in or we double the number of transistors, our performance should double. But that is no longer happening. That is not happening, right? My processor, which let's say I bought last year and I buy this year, does not double in frequency, does not make my computer 2 times faster. Right, then what is the point of packing so many transistors? That means we are not effectively using all the transistors that are available to us or given to us. Technology advancement in terms of packing transistors is happening, but we are not utilizing it well. Any guesses why? Any thoughts?
Because we are
We don't
not
have the
expecting.
necessity.
We don't have the necessity. We don't have the necessity.
Because we are not utilizing the so many functions these transistors are providing.
We don't have the necessity. Why do you think you say that? Now, if I want to run some program, let's take the very popular deep learning application, right? Any deep learning application, we say it takes 1 hour to do training. I mean, if I could do it in 1 minute, oh, it would be fantastic. Is there no necessity for performance?
It has reached saturation.
It has to?
No, I'm saying it has reached saturation.
Yeah, but why?
And power on all the transistors at once at a reasonable amount of power.
Mm-hmm. So there is a power envelope that we have to work within, so we cannot exceed our frequency of operation. Okay, what else?
MOSFET channel length is now 6 nanometer or 7 nanometer. So it is.
Okay, operating frequency is limited by that. Okay, but performance is not just frequency. Performance can be, the total time taken for a given application to run. Okay, frequency is limited, but are we limited only by frequency to expect performance? What about parallelism?
We are unable to utilize all the resources we have put into the into the same area.
Correct. Yeah. And why is that? I think that is what we will look on in the next few slides. Right. So we are not able to make use of all the transistors that have been given to us because these transistors, after all, have been put together in a certain fixed architecture, and we are trying to exploit application performance through the way it is arranged, right? The microarchitecture is nothing but an arrangement of transistors in a certain form, in a certain fixed form. So what are we seeing? There is a problem here. There is a problem in terms of the computing energy. And if we were to look at the number of cores on the x-axis and the energy efficiency on the y-axis, CPUs go a short distance in terms of how many operations can be performed in a milliwatt. We can go a little farther with CPUs and GPUs. A little push can be given to us by DSPs, digital signal processors, which have custom hardware in them to accelerate applications. They get slightly more energy efficient. But at the end of the day, if we are looking at significantly better performance, we have to move towards what are called dedicated hardware or custom solutions or custom accelerators. If you are looking at 1000x energy efficiency, the only way we can achieve that is by going towards dedicated custom solutions. What do I mean by that? We will need to look at what is the application and what is the hardware. Does the hardware or the transistors, are the transistors effectively using, are they being used effectively for the application that you are running, right? Currently, all these architectures that we were looking at, CPUs, GPUs, are all general purpose architectures, right? CPUs primarily are meant for general purpose processing. GPUs have customizations for extremely operations, very fantastic for parallel applications, image processing, etc. But what happens if we look at other applications which are don't fit into these um, in terms of these characteristics? We need to make sure that whatever is the application, our transistors are meant to run those applications, which are only possible through dedicated hardware. So when I say dedicated hardware, what do I really mean by that? We want to look at algorithms and building architectures that match these algorithms. Algorithms can be diverse. We are talking about maybe graph applications, which are different from image processing applications, which are different from maybe encryption algorithms. They are different, right? Each of them are different. So why not think of building architectures or customizing architectures to meet the algorithms requirements? So if we have, say, we know a priori that we want to run a bunch of graph algorithms, then we should be thinking of building something like a graph core, right? So my processor now is fine-tuned to run graph applications. It has instructions which are very specific to graph-related operations. It is not a general purpose core, it is a graph core. Or for example, I have a lot of matrix multiplication kind of operations, linear algebra operations. Then why should I look at a general purpose core or a instruction set architecture which caters only to general purpose application? I clearly know that I have maybe vector kind of operations. I clearly know I have array manipulations. Then I build my processor accordingly. Or on the other hand, if it is a DSP application, then I know, okay, I am only doing A, B, C kind of instructions. I don't need other instructions. Or I can build I can define my own instructions and build an FFT engine. So that's what is the whole concept of building architectures which are specific to the algorithms. In this context, I want to bring in FPGAs as competitive architectures to existing traditional conventional microarchitectures. Right? FPGAs are only placeholders here. They are they are representative of a wide class of architectures that can be called dedicated hardware, custom hardware, or architectures that can be customized during deployment. They are also representative of programmable hardware that can be customized for application specific behavior. Okay, so we are talking about moving towards custom hardware, And is this something that I'm talking out of the way? Is this something, people have not thought about? I don't think so, right? So this has been around for a while and it is going in, a very, very interesting direction now, because we've had Intel that acquired Altera. Altera was primarily a programmable FPGA device vendor, right? So Altera was purely FPGA company that was bought over by Intel, and this is, I think, 5 years ago, 5 or even more, 7 years ago. Now Intel is seriously looking in terms of programmable solutions. Programmable solutions are nothing but building architectures, building accelerators for applications under consideration. Whichever application is being run, how can we build custom accelerators? Is Intel the only one that's doing it? No, even AMD is in the process of acquiring Xilinx. Xilinx is the other big vendor for programmable devices. And is that the only thing? No. Google also came up with tensor processing units for deep learning. TPU will be handled in the next hour. Sparsh will be talking about TPUs. So again, to emphasize the fact that there have been alternative architectures that have been coming into the market to challenge existing processing architectures, be it CPUs or GPUs. There has also been something from Amazon for deep learning application. I think that was Nirvana. And even Microsoft is talking about FPGAs, and it's not just talking about, it's deploying FPGAs in data centers. It is deploying FPGAs in edge equipment, etc. Right? So FPGAs are programmable hardware that are very suitable for custom hardware acceleration. So custom application acceleration are very, very well doable, feasible, viable through the use of FPGAs.
Excuse me, ma'am.
Yeah.
Ma'am, but where are they used? I mean, in daily needs, majority of the people would not need it, and for high-end applications, we have supercomputers. So where do they exactly fit in?
Good question. So where are they being used? You'll be surprised to hear that FPGAs are there in today's cell phones. FPGAs are not far away from being incorporated in high performance laptops, desktops. They are there in cloud computing environments. They are very much around in supercomputers. So everywhere where you need acceleration, wherever you need performance, it is being used. It is simply that it's not, we are not aware of it. DSP applications, they have been being used for decades now actually. Where else? Networking applications, routers, etc. Very, very easy if you open up a box to find an FPGA device there. For packet processing, etc., FPGAs have been around. To give you more concrete examples, sorry, you said something?
No, ma'am, I said Bing.
Yeah, Bing. Yeah, you're very right. Yeah, Bing is Microsoft's Bing has it's that search engine accelerator which uses FPGAs. Yes. What else uses FPGAs? Yeah, if you were talking about supercomputing environments, it's been around for a while. Let's say applications like molecular dynamics simulations, very well suited for FPGAs. Genome sequencing. I think the latest device from the topmost vendor from in genome sequencing, Illumina, is actually shipping devices, systems with FPGAs. They say they only get the horsepower through FPGAs. What else? Yeah, financial computing, stock market fluctuations, etc. Very quick response computing, where you really need to have really fast response time. FPGAs have been around for nearly 20 years now. Okay.
Okay, ma'am.
Once we are done with say the prototyping and checking if the FPGA or like synthesizing a particular architecture on the FPGA for some algorithm, won't we design an ASIC for production purposes? Like, do we still use the FPGA also production, or do we convert it to an ASIC and then?
Yeah, good question. So FPGAs came into, I mean, existence, or let's say um, the whole concept of programmable hardware came in maybe about 50 years ago as prototyping devices. Yeah, they were meant to be used um, initially as glue logic. Glue logic is like, let's say you have two devices on a board and you want to interface these two devices, but let's say one of them has a active low, another has a active high signal or something, and you want to make these quick translations. You put in an FPGA or a CPLD, what it was called those days, and you put in all these glue logic kind of things, and it was used. FPGAs, I mean, gradually went into being prototyping platforms because you could modify what is run on an FPGA. You went in before developing an ASIC. Let's say you have a processor architecture, you put it on an FPGA, you boot an OS, you validate that everything is fine. Of course, it will not be running at the same speed at which you expect the ASIC to run, but still, functionality wise, you have hardware validation, right? This is hardware validation. And then you went on to develop ASICs. That is not the primary market now anymore. FPGAs are being used as compute resources as is. They are not only used as prototyping environments anymore, simply because of programmability. You have the possibility to say, okay, now be a graph core, now be an image processing engine, now do something else, right? That flexibility of in-field programmability is making it very attractive for FPGAs being used as is, as compute, serious compute devices. Does that answer your question?
Oh, okay, ma'am. So, like, does the architecture, change on the fly even in mobile phones and everything, or because I assume everything was completely fixed.
I didn't hear you well, but to give you an example of whether things change on the fly, let's say you have a new um, standard that comes along, maybe for your application that you're looking at in your mobile phone, you have a, I don't know, some, um, I don't know, an encryption standard or something, right? That has been updated. Now you don't need to throw away your cell phone, or you don't need to throw away your network equipment to adapt to the new standard. You can simply reprogram the FPGA wherever it is sitting through through its programmability features, so that you can update your FPGA to behave or to accommodate this new algorithm. That is one possibility of one case where in-field programmability becomes very useful. Did that answer your question?
Oh, yes, ma'am. Thank
So there is a question I missed. What is the difference between an ASIC and FPGA? Just give me a minute, I'll get there. Okay, so this is basically to motivate you to look at alternative structures to see what is it that can be done to improve performance. Can we, is there, I mean, are there compelling reasons to break away from the traditional thought process? Are there advantages, etc.? Okay, so in the rest of the talk, I will try to bring in some differences between traditional CPU-like architectures, microarchitectures, and contrast it with FPGAs. CPUs mainly talking about ISAs from ISA, general purpose ISAs based architectures from Intel, AMD, etc., versus FPGAs from Intel, AMD as well, right? So that will be a few, and then the next few slides will be about this. So we are talking about two distinct domains. On one side, we have processors from vendors like MIPS, ARMS, TI, AMD, etc. And on the other side, we have FPGAs from vendors like Xilinx, Altera, etc. What do we mean by these two domains? One of it is the processor domain, where we have temporal computing, where we have the traditional form of processing where we say things change over time. Yeah, and we are constantly trying to extract instruction level parallelism and build architectures that facilitate instruction level parallelism. Right? And when I say temporal computing, what I mean is we are talking about the traditional pipeline where you process each instruction through an instruction pipeline where you fetch, decode, read or write from the register, send it to the ALU, send it back to the data memory or register. Right? So this is the way things flow in an instruction set architecture based system, which is the processor that we have in mind. This kind of processing is temporal computing, right? You go over time and you repeat the same thing over time. Resources are being shared over time. Whereas in FPGAs, it is different. We are talking about spatial computing. We are not talking about reusing resources over time, but we are talking about spreading out computing over space. And in this context, since we are using transistors, according to the application given to us, we have parallelism that is only limited by the application. Now, if my application has, a bunch of operations that can be done in parallel, I can have an architecture that does all of this in parallel. I'm using the transistors to actually replicate the application. What do I really mean by that? I am given a playground. Okay, FPGAs are considered as programmable playgrounds where you have a bunch of programmable resources. Let's say we call them functional units and they have some kind of memory. Let's call them flip-flops for now. And each of this functional unit can behave according to what you define it to be. So for an example, it can be an adder, it can be a multiplier. If you don't have adders and multiplications, you have only other logical operations, it will behave as a logical operator. Or you have, some Galois field arithmetic, or, some other kind of arithmetic, or you have only trigonometric functions, whatever, you name it, and it can behave like that. That is programmability. And what else? You have a sea of such functional units. So you can actually have as many number of such operators as you need in your application. So this is what the transistors on this chip are being used for. They are being used to define operators that match what is needed in your application. Okay, so for example, if I have a graph application and I have to store a graph on chip, and then I have to make continuous, I need a lot of comparator operations, then my functional unit will be a comparator and my memory on chip will be used to store that graph. Now let's say I have a different application where it is an image processing algorithm. I use my memory to store the images in whatever format, and I have operations that are very specific to what is needed in an image processing algorithm. Okay, so this is the way transistors are being used on an FPGA. They are spatially distributed, they are spatially available, so it's called spatial computing. There is no reuse that happens over time, like in the case of instruction set architectures where we are following the instruction pipeline. Right here, operations happen as and when required by the application. So basically, it's a completely programmable device where you define what is the functionality, what is the arrangement of compute and memory, how many compute units do you need, what is the type of memory you need, what is the connectivity between your compute and memory, etc., can all be user driven, which leads to user defined parallelism. So what I really mean by that, now let's say I have an application which looks like this. This is a, let's say, a graph which has
हेलो
could you
अरे
please
वो हम बोल रहे थे कि छवि का भी पॉजिटिव आ गया है तो हम लोग का सील नहीं खुलेगा हम्म
all right, sorry about that. Okay, so what was I saying? We are let's say we have an application which looks like this. Yeah, I have a number of operations and there is some kind of dependency, and finally I have an outcome. So I have some inputs arriving, I have to perform some kind of operations, and then I have an output. Now, how is this performed on a processor? I have a ALU and I have to do it one after the other. Okay, so it's a sequential operation no matter what. I mean, I can maybe improve on ILP marginally. I can go up to 1, 2, 3 in terms of parallelism in ILP, but my operations may not be a single operation, a single instruction. My operation may comprise multiple instructions. Whereas on an FPGA, I'm not limited by that. I'm using the entire area to perform operations I need. So I'm only limited by the dependencies within my application. You see the difference? So I can implement operators as is. I use the entire area. I use the entire number of transistors available to me. I uh, configure my FPGA logic to perform these operations, and I map the application as is. Of course, there are limitations in my application itself, which limit the number of time steps needed to perform, but they are way shorter than what you would expect on a processor. So the latency from the input to the output is definitely lower on an FPGA than on a processor. So the number of clock cycles you need are definitely lower on an FPGA because you are configuring custom operators which are not limited by the microarchitecture of the device that it's running on. Okay, so we are looking at comparing temporal fixed architectures versus spatial configurable architectures. On one side, we have user-defined parallelism, right? We can use 2 functional units, 3 functional units, merge them, define whatever is your parallelism needed uh, that can be exposed by your application. We map it onto an FPGA. It is extremely flexible because you can change your operator based on what is your application. And as a result, you get better performance per watt. Yeah, you're making use of all the transistors that are there, which gives better performance and better energy efficiency. In contrast to limited parallelism in processors and the main constraint that it's a fixed architecture. You cannot modify the LU, you cannot modify the pipeline, you cannot modify any of the instruction set architecture that has been implemented. Of course, you very well know that scalability of processors is also under question because you can scale for 1, 2, 3, 4 processors, and then you need a different hierarchy. Are we able to exploit instruction level parallelism after putting in multiple processors, right? So that is something to worry about. Right, so application mapping has now changed paradigms, right? So we are talking about starting with an application and going on to a device where we go through multiple stages of transformations, where we define the algorithm, then decide on what is the programming language, apply optimizations which are specific to the architecture, or develop your own architecture. That is when it becomes a custom hardware and you have to fabricate that device. This is the typical design flow when we are talking about application specific integrated circuits, right? You start with hardware design. You start with hardware design, you perform multiple operations like transformations like logic synthesis, technology mapping, placing, routing, and fabricating the device, which is what makes it application specific integrated circuit. As you can see, it's a huge design effort. So if I want to develop an ASIC for every application, I have to go through this entire design flow, which means it could take me 1 or 2 years till I have an ASIC for my new application. So if I have a graph algorithm, I need a graph ASIC, I have to go through this entire flow. It'll take me a year. And then I have suddenly a new algorithm, then I have to go over the entire process. It'll take me another year. And in the meantime, I have, the market has gone way beyond. My competitors have already, caught up with other kind of devices. So ASIC, I hope that answers the question. ASIC is fixed hardwired systems, hardwired devices which are customized for your application only. Whereas, as you can see, this is not viable. We need something that can bypass this phase of fabrication, which is where FPGAs come into play. FPGAs are off-the-shelf available devices that take your design and allow you to configure the device. As you can see, the design effort, there is design effort. You still have to comply with all the previous phases. You have to define hardware, you have to do logic synthesis, technology mapping, placing and routing. But that advantage that the FPGA is a device that is, you can simply buy it off the market and you can use the same FPGA device for different HDLs makes a big difference. Nevertheless, the rest of it is also a concern, right? So we have, if I were to compare this with how things happen on a processor, it is almost effortless on a processor. Let's not deny the fact that mapping an application onto a processor is pretty seamless. You write your code in your high level language. Of course, there are methods of parallelizing it. There are some programming language level details that you need to get into, but taking a high level language, putting it onto a processor is simply a compilation process, which is very straightforward as compared to what happens on an FPGA. So the process of going from an application to the device is very, very straightforward on a processor, which makes it very, very friendly, user friendly, market friendly, all of that. And that is a strong, very strong reason for seeing market success with processors. But we are far away from all of that in FPGAs. What takes, maybe a single time step, even in specifying the application in terms of functionality, could take way longer in an HDL. So if I were to tell you, please write, an application, graph application in C or C++, versus saying, okay, can you describe the hardware design for a graph application using one of the hardware design languages? It would take way longer. That's a known fact. And that is one of the reasons for popularity of processors as compared to FPGAs. FPGAs were not friendly for programming, so they were not ready for the masses. FPGAs or reconfigurable computing for the masses is still a long way. So if I somehow get by for describing the application, I still have hours of time or compute that is needed to perform logic synthesis, technology mapping, placing, routing, until I have a working version ready on my FPGA. Yeah, I say this all the time. What takes a few minutes could take a few days. And we have, in the lab, we have this all the time. We had a communication algorithm that, actually took 1 week to synthesize. And there were some other applications that, students were working on, and they would say, yeah, I'll come back to work when it's synthesized. So synthesis time is non-trivial. It takes way too long. Right? So there has been efforts. Yeah, is there a question?
Like FPGAs are also like very slow compared to processors, right? So right now,
Yes, you're very right. FPGAs are very slow in terms of frequency of operation. The frequency, so if you see a processor that operates at 2 gigahertz, the best frequency that you can get on an FPGA is probably below 1 gigahertz, right? So, but please remember, high frequency operation is needed when you are doing a lot of sequential computing, right? You're doing one after the other, so you need to do it really quickly. But if you are doing things in parallel, you don't need to be so fast. You get the point? Does that make sense? Yeah. So I will come to some concrete examples to show you how frequency is not a concern in comparing performance of an application on a CPU or a GPU versus on an FPGA. Okay, so yeah, so first of all, the problem at hand is how do we handle this, initial design time that goes into developing an application. So hardware design languages have been increasingly replaced by high-level languages. They can be directly used on FPGAs. So for example, we have languages like System C, C++, OpenCL, etc., that are now that have very well established design flows that can map directly onto an FPGA, right? So if you have an application that has been designed in written in C or C++ or OpenCL, you can use it directly for mapping it onto an FPGA. So what is the advantage of this? This is called high-level synthesis, which takes your high-level language directly to hardware. We are able to see significant improvement in design time. So if you look at design time on the, if we were to compare design time versus application performance, and we are looking at a bunch of devices here. So what you see as gray dots are the first working versions on 3 different architectures, maybe x86, a DSP, and a GPU. And that same version, working version on an FPGA, it could take a little bit till you have the first working version, which may actually exceed a typical design cycle in a software project. But if you look at, the optimized version in the current form, it is much better in performance as compared to all of the devices, right? Even GPUs. If you look at that in that one, x86 DSP GPUs, an FPGA implemented with RTL, that is hardware description language, can exceed performance. But maybe you don't have all the time to develop a design in RTL. Spend 1 year developing RTL instead of developing it in 1 month on a GPU, and you only have marginal performance improvement. So high-level languages with high-level synthesis make this effort easier. Now, what was taking way too long is viable with high-level synthesis. So what you saw with x86, you can reuse the same code, pretty much the same code with FPGAs, but it gives you significantly better performance. So even the first working model with high-level synthesis is much better than what it is with CPUs, GPUs, and DSPs. And of course, if you play around with the tool, play around with optimizations, you get definitely better performance with even less effort as compared to DSPs and GPUs. Yeah, so FPGA design entry tools are becoming very powerful. They're making it very easy for software kind of programs to be mapped onto mapped onto FPGAs. Right, so they provide pragmas, etc., that help you to improve latency, improve throughput, reduce area requirement, and also improve device utilization. So the way it works is these are pragmas which can be directly inserted in the source code, just like how you did OpenMP uh, programming or any pthread kind of programming. You have pragmas in high-level synthesis. Within high-level synthesis that let you manipulate the C code to run in parallel as compared to the sequential execution that it was written for. Yeah, the similar kind of ideas of unrolling, pipelining, etc., can be introduced through pragmas in the source code itself. There is also special attention paid to arrays, etc., because you have unlimited resources here. I mean, they're physically limited, but pretty high as compared to the requirement of most applications. Okay, so that's about high-level synthesis. And moving on to what is it that makes FPGAs different in terms of the architecture itself. Right, so FPGAs, so far I said it's programmable logic. It is a lot of transistors that is customized, and you can think of it as a playground, etc. But what is it really made of? You can think of it as a grid of configurable logic blocks. That's how it was traditionally, or maybe 20 years ago. It was a homogeneous grid of configurable logic blocks, but today it has high density memories, RAMs, it has custom ASIC blocks called DSP blocks, and it also has recent advancements have included special operations which are ASIC like operators for machine learning, or it can be for other custom applications. Now, let's say if I were to take this fabric and map a processor onto my fabric. Now, it's a configurable fabric, right? So I can map anything. Now, let's say I decide to map a VLIW processor on it, just to keep you thinking. You have studied VLIW in the past few days, right? A VLIW processor has multiple ALUs, and it can process multiple operations in parallel, and it has all other things like the instruction memory, data memory, register file, etc. How do I put all of this onto this fabric? I will put my instruction memory on the high density memories that are given on my FPGA chip. I will put data memory also on that, and any register file, as long as it is up to two port register files, I can accommodate it on the block RAMs. Everything else, like the adder, the shifter, the multiplier, can go on to what are called as DSP blocks, which are dedicated hardware. So you have dedicated multipliers, shifters, etc., available in the playground or in the configurable logic fabric. I will use that, and everything else will go on to the configurable logic on the FPGA area. Right? Other things like multiplexers, control logic, state machines, etc., can be mapped onto the configurable logic that is given to you. So, for example, I mapped a VLIW processor. I want to understand what is runtime reconfigurability or on-the-fly programmability. What it really means is, let's say I use a section of my FPGA device to implement a crypto processor. So I put in a crypto processor. I use the configurable logic and maybe some block RAMs and DSPs. I can also put in an image processing algorithm on to the fabric. I have dedicated locations for it. And let's say I put in an Ethernet controller. This is how my FPGA fabric looks today, maybe for a certain customer. Yeah, the device is given to you. You have, put these algorithms onto the device. Now, for a different vendor, maybe I have something else. I have a graphic processor, I have some gaming application, and maybe a processor for whatever reason. It is doable. Or let's say the same customer decides to have something else. I can do that on the fly. This is runtime reconfigurability. Yeah, this is the added advantage that you get with a configurable logic fabric.
Excuse me, sir.
Yeah, yeah. Go ahead, please.
Sir, you had told me to send the applications, and you had asked me to call you, but you didn't pick up the call.
Oops, this is not for me.
Oh, I had told you now that I had got an internship and you asked me to send the application.
Please remind me because so many things I'm.
Okay, so no internships. I didn't ask. Okay, fine. So what was it that I was talking about? This is runtime reconfigurability. Now, moving on. Does this really mean it gets better in performance? Does this really mean that it makes it fantastic? Is I can get better than all kinds of processors? Not really, right? Let's say I put in a graph where I compare processors
Ma'am,
and FPGA.
ma'am, can you explain what is the DSP blocks and what
Yeah,
exactly it is?
yes, I will come to it in just 2 more slides. Is that okay?
Okay.
Yeah. Okay, so if I were to, plot a graph of saying how does this help in terms of performance and how easy is it to use these kind of devices, no matter what, in terms of ease of adaptability, processors are at the peak, right? You take an application, map it onto a general purpose processor. You can map any application onto a general purpose processor. They are very, the microarchitecture, the compiler tool frame is meant to be used for all kinds of applications. And if I were to put an ASIC in this same context, it comes to be the best in terms of performance. There is no way to beat ASICs at one end and processors at the other end. FPGAs come somewhere in between. There is a trade-off at performance. You're not as good as ASICs because you don't have dedicated hardware, you have programmable hardware, but you're better in performance as compared to processors, and you are not as easy to program as processors, but definitely easier than using ASICs. So we do see a performance gap of about 5x in terms of speed, area, and power as compared to ASICs, but we are definitely better in terms of area, speed, and power as compared to processors. So to answer your question, I think I missed this question. How is DSP different from GPU, CPU, and FPGAs? What are the application cases in current scenario? So DSPs have specialized operators that have been implemented. For example, DSPs have dedicated multiply accumulate units. They have, let's say, for running FFT kind of applications, FFT FIR filters, you have operators that have been added in addition to CPUs that are meant for general purpose, entirely any kind of application. DSPs are more fine tuned for signal processing kind of applications, meaning there are operators that are found frequently in DSP applications that have been included in the microarchitecture. How are GPUs different from DSPs? GPUs, like you saw in the previous lecture, have massive parallelism. You have very many processors available in parallel. You can have multiple threads that are running in parallel, where each of the thread is still running on a processor, right? It still executes instructions. So that way, GPU is different. FPGAs are entirely configurable, which means you don't have the notion of an instruction on an FPGA. You define what is the operation that you want and you configure it to perform that particular operation. I hope that answers your question, Anmol. All right, so let me know if there's a question. So how does the FPGA architecture actually look? To answer what is a DSP block, what is a programmable logic, etc., let's quickly dive into the architecture. So the architecture or the playground that I said is internally structured like this. Okay, so you have a set of really well-defined resources. They are programmable logic. Seen in blue, there is programmable routing, and the gray is programmable IO. Right. So programmable logic. What does it mean? Programmable logic are mainly made up of what are called as lookup tables. They are memory-based functional units where each lookup table is nothing but an SRAM and connected to a multiplexer. By use of this structure, you are able to implement any function. So if it's a k input lookup table, you can map any k input function. What do I mean by that? In the interest of time, I'll just skip a couple of slides. So if it's a 2-input NAND gate and if it's a 2-input lookup table, I only have to fill in my truth table in the SRAMs. So I get a 2-input NAND gate, and if I change the truth table, if I put in different values, it can be a NAND gate, NOR gate, whatever, right? Any 2-input gate. But at the same time, I know that my lookup table is now significantly bigger than what would have been on an ASIC. So a NAND gate would be roughly 40 transistors using lookup tables as compared to 4 transistors in a custom ASIC. And this is huge, but this single structure gives me extreme flexibility to behave as anything. It can be a 2-bit ALU, it can be anything. It can be an adder, subtractor, whatever. If I have a 4-input lookup table, I know I can implement any 4-input function. So there are a few design decisions that have been studied before deciding on the size of the lookup table. So when I say an FPGA has a 5-input lookup table, these are analyses that have been done over a set of benchmarks that make it viable to accommodate a wide range of applications, right? So you have a single FPGA fabric that should accommodate a wide variety of applications. Yeah, only then it becomes beneficial. So people have looked at a wide set of benchmarks and have arrived at the fact that a 4, 5, 6 input lookup table is what is fantastic in terms of trade-off between area and delay, right? I am going a little quickly to keep up time. So if you were to look at area itself, a 6-input lookup table seems a good decision in terms of area delay trade-off. So you have the basic logic element of the programmable logic structure that has 6 input lookup tables. I think 7 have also been appearing in recent architectures, but there is a price you pay. And what does it look internally? You have a lookup table and a flip-flop which are connected so that you can map any logic, any function onto the lookup table. And if it has to be synchronized, you can use the flip-flop. So you have a choice of using it asynchronously or synchronously, combinatorially or sequentially. That multiplexer there is programmable again to allow you to maybe combine multiple lookup tables or restrict the critical path of your design through the use of the flip-flop. So that's your basic logic element. Of course, you put in many such logic elements together in a cluster, and you have to pay attention to the cluster size because it could grow exponentially, because with multiple lookup tables, you have more SRAM cells, more multiplexers, more interconnectivity, etc. Nevertheless, there is again study that indicates the choice of the lookup table around 6, etc. are good, and the number of lookup tables in a cluster, about 4, are optimal for delay as well as the number of logic blocks, right? So this is a study that shows that there is not much improvement in the critical path when increasing the cluster size. So typical cluster sizes are around 3, 4, which is here. Okay, so there is diminishing returns beyond cluster size of 3, 4, and then LUT size of 6, lookup table size of 6 is found to be optimal. All this is about the programmable logic, which is configurable, etc. Now, if I show you a snapshot of how this logic looks, it has multiple lookup tables, a bunch of multiplexers to select, and also few flip-flops. In addition to programmable lookup tables, there are also memory blocks in today's devices. They can be configured with variable width and depth. So you can have, let's say, a 2x20 memory or a 10x10 memory, etc. You can decide the width and the depth of your memory. You also have the choice of making it single port, dual port, FIFO, etc., right? Depending on what is needed in your architecture. In addition to that, we have what are called as DSP slices. DSP slices are nothing but operators that are found to be frequently used in most applications. You can think of it as your own ALU in your processor. Yeah, it has all these operators, multiplier, adder, accumulator, some logical operator, even a pattern detector, etc., which have been implemented and embedded into the fabric as custom hardware. So these are small ASIC operators. ASIC, I say that because they have fixed operations. You cannot modify these operations, and there are very many of these available in the FPGA fabric. I'll come to the numbers in a bit. So to give you an idea, recent advances also have AI specific operators that are included in the FPGA fabric. So Intel's, not even the recent, I think couple of years ago, they had 8-bit operators included in the fabric so that it can become advantageous for matrix vector kind of operations, or even inferences, 8-bit inferences. Right, advances have led to including flip-flops, ADCs, DACs, security algorithms. There are small IPs actually integrated in the FPGA fabric. So much so that there are even hard processors that have been built into the FPGA fabric. So there is a quad-core ARM in one of the processors, and a few years ago there was even, which is still around, a GPU also in the fabric. So the FPGA itself has gone far ahead and become a system on chip by itself. Okay, so does that answer your question? What is a DSP slice?
Yes, ma'am.
Okay. So this is all about logic, right? We have, all kinds of hard blocks which have fixed functionality, and a whole bunch of configurable logic blocks which are lookup table kind of functional unit that can be configured according to your application. In addition, we also have programmable routing, which facilitates connectivity between these logic blocks, right? So your application may have different requirement. You may need 2 blocks, 3 blocks, 5 blocks, whatever, right? So you want to use all the logic blocks as a single functional unit in your application, and that should be viable through routing, which is again programmable. Programmability allows you to connect logic blocks, connect IO to logic block, and have different kind of flexibility to support short, long wires, etc. Okay, so
Excuse me, ma'am.
yeah.
Ma'am, once we program any processor or something to an FPGA, how are applications written for that specific processor?
Good question. So you're talking about this part, right? Let's say I have a processor, and how do I write applications to it? So it becomes a hardware software co-design where you write applications in software languages, right? The same kind of way you write for processors, and you can use this as a host processor and offload your acceleration or your hotspot onto the FPGA fabric, which can be offloaded through the processor. So you write C code. Nowadays, you can write everything in C. So your host code is in C, your kernel code is in C, and the kernel code goes through high-level synthesis, which is implements it as an accelerator coupled to this processor using high-level synthesis.
Okay, and in the previous one example, you were showing about reconfigurability of FPGA.
Yeah.
So you had shown that you are programming a game application onto that.
Yeah. Mm-hmm.
So it is kind of permanent thing, isn't it? I mean, we cannot have multiple games in that.
So again, where do you put that, right? If you put it on a programmable fabric, finally, it is only about connecting those logic blocks in a certain fashion to achieve the functionality. So it is still changeable.
No, not in the sense of changeable, but in the sense of we cannot have a large number of games, right? Like in phone we generally have lots of games and they are kept in the main memory. But in the case of FPGA, if I keep on programming the FPGA with different games, so one thing is like the size is of course very less for let me say 100 game. Oh,
Yeah,
okay,
okay.
why not program it for 100 games?
Yeah, I got your question. So programming, no matter what it is, right? Is it a game or is it a processor or whatever, is a sequence of ones and zeros, a binary that sets or resets the lookup table, the flip flop, the memory, etc. Do you agree? It's, basically you have to say what is the sequence of ones and zeros to achieve a certain functionality. This is a binary, it's called a bit stream. Okay, if you have a bit stream for chess, you have a bit stream for, I don't know, Go, you have a bit stream for some other, I don't know, tic tac toe, etc. Wherever it is, even if it is stored off chip, you can always get it and program it. You only need a bit stream to configure the functionality. So just the way you have, you store it off chip and then um, use it on a processor, here you can call the bit stream from off chip and program it whenever you're using it.
Okay, so can it be a kind of multi-processor thing? Like suppose there are two games, game A and game B, and I'm let me hypothetically say I'm playing both the games at the same time. So can it be done like this? Like FPGA, in one part of the FPGA the chess is running, and another part of the FPGA something else is running, some other game.
Yeah, as long as you have, you can make sure that chess fits in, physically fits in the FPGA. You have a big device. Yeah, you can. I mean, as long as resource is not a constraint, you can achieve the functionality independently.
Okay.
Does that answer your question?
Yes, ma'am.
Okay. So maybe we'll hurry up a bit. I guess I'm running out of time. Okay, so I was talking about programmable routing, which is to support all kinds of connectivity. And to facilitate that, we have different kinds of structures like connection boxes and switch boxes, which basically are multiplexers to switch the route in the right direction and make the right connectivity. Again, this is programmable because you set or fix, you put in a 0 or 1 to say that there is a connectivity or there is no connectivity, right? So these are structures available and you can program them accordingly. And that's about routing. There are also different kinds of wires in that, so that you can use short wires that hop a single block or long wires that go around hops of multiple blocks. And then finally, you have programmable I/O. So you can define different types of interfaces based on your requirement. Okay, so different kinds of IOs that are feasible is, interfaces to memory, interfaces to, standard interfaces, gigabit Ethernet, etc. are all, you can configure them according to your requirements. So these are not fixed. You can fix them as per the application where the FPGA is being deployed. All said and done, I want to give you an idea of how today's FPGAs actually look. So looking at, so a quick reality check, right? So I have a bunch of FPGAs here. These are from Xilinx, and to give you an idea of what is the kind of complexity that is available, maybe just we'll quickly look at, so there are different kinds of resources available on chip, right? So we have multi-processor system on chips available in some of the devices. There are DACs, there are other for error correction codes, etc. But let's look at memory and let's look at DSP slices. Okay, and if I were to look at DSP slices, now one of the high-end FPGAs has about 4,000 DSP slices given to you for to use it according to your application's requirement. So imagine having a DSP performance of 7,000 giga operations, giga max per second on a single device, right? And there is there is really high speed interface also viable, about 1,000 gigabits per second. And there is also present day FPGAs which have memories available, located very close to the fabric itself, which makes it, with high bandwidth memory, etc., which makes moving data on chip and computing very, very simple. So if this is the kind of 4,000 operations that can be run in parallel on a single device is something that you're thinking of, frequency of execution is not a concern. Does that make sense? Even if the FPGA operates at lower frequencies, you're still way off in terms of number of operations that you're actually performing in parallel. Right? And what is the kind of logic that is available? We have, 1,000 up to 1,000 kilo cells. Think of them as each of them being about 4 lookup tables. So that is the kind of functionality, that is the kind of, massive parallelism that is available on chip. So that is the way transistors are being utilized in FPGAs, right? You have different kinds of cells, you have on-chip memory, you have compute in terms of DSP slices, you have I/O in terms of all kinds of interfaces which can facilitate parallel or spatial computation. Okay, and quickly moving on to some examples to bring out the differences between CPUs and FPGAs. GPUs and FPGAs. So let's look at one recent work, actually a couple of years ago, by Intel, where they compared. Am I audible?
Yes, ma'am, you're audible.
Some question has come up. No. Okay, so what is it? How does it compare to state-of-the-art GPUs? So let's say the peak flops, floating point operations in Titan is about 11 single precision floating point operations, whereas the FPGAs from Intel have about 1.3, and a slightly higher end has 9.2. So in terms of floating point operations, it is not as much as a GPU, but hold on, look at what happens. On-chip memory is higher, and let's say memory bandwidth is the same. When we look at floating point operations, what you see here in the graph is these are the two FPGA devices, and this is the theoretical peak that you see in dotted line, which says that in terms of floating point operations, yeah, GPUs are way better. But when I say floating point operations per second per watt in terms of energy efficiency, FPGAs reach out higher. Okay. And then when I start to look at irregular applications, right, where I can't run everything in parallel as I would expect on a GPU. GPUs are fantastic as long as I have very parallel applications. FPGAs work way beyond the peak achieved by the GPU, right? Please note that the operating frequency is still very low, 300 megahertz, 500 megahertz, 700 megahertz, compared to few gigahertz on Titan. Right? Even despite the fact that the frequency is low, I'm able to achieve higher teraops per second. And needless to say, per second per watt is also.
Ma'am, here we are comparing the algorithm. What should I say? The architecture of GPUs and FPGA, isn't it?
So we are comparing GPUs and FPGAs for a particular application, which in this case is deep learning, deep neural networks.
Okay, so GPU may also exceed FPGA in some cases. In some other.
Yeah, it is clearly, here, please look at this. When it comes to pure floating point operations, there is no beating GPUs, right? If I'm looking at floating point 32-bit, yeah, I'm definitely GPUs are better. But when I get into energy efficiencies, FPGAs are better. And then when I look at applications, the same application that is sparse. When I say sparse, I can't run, it's not SIMD-like operation where I'm running the same instruction on all kinds of data. I may have divergence, I may have, synchronization issues, etc. when I'm trying to improve the utilization in GPUs. That's where FPGAs come into play. Also, they come into play when I am looking at um, odd bit widths. Let's say the native bit width in a GPU is, let's say, 32-bit or 16-bit, but I can go to any bit width in an FPGA, right? I have configurable operators. So if I look at, I say I want 6-bit operations, I can do that very easily on an FPGA where I beat the GPU because of fine tuning my transistor usage through configurability. Of course, GPUs are definitely better when we are talking about, pure regular operations that are 32-bit floating point operations, etc. Does that answer your question?
Yes, ma'am.
Okay. And going further, if we are looking at, binarized deep neural networks where operators are actually, single bit wide, there is no way we can achieve that using GPUs because the operators there have fixed bit width and you can have your custom bit width here in FPGAs. Okay, so to kind of summarize, there is a place for each kind of operator in the diversity of applications. I mean, it's never to say that, FPGAs can beat all kinds of processing structures that have been there. There will be a place for CPUs, GPUs, TPUs, and FPGAs in computing environments. That's why we are moving towards heterogeneity and heterogeneous computing, where we say that CPUs will be there, they will be useful in sequential irregular workloads, GPUs for very parallel workloads, TPUs for matrix kind of operations, and FPGAs for custom operators. Right? So there is a place for all of them. And to give you an idea, other algorithms like CNNs on FPGAs were, implemented, and they gave you orders of magnitude improvement over CPUs. For applications like genomics, there were, a 70x speed up that was a 70x, right? Over 70 times over CPUs because of, the custom bit width that was made possible. And then, some other applications that we tried at our end with, even without, heavily coding it in hardware or so, even a C-like program gives you orders of magnitude better performance. The same is true for graph processing. So what next? Heterogeneous architectures are something we should expect. There will be cooperation, cooperative execution between CPUs, GPUs, FPGAs. There will be custom structures. It will be there, in data centers, etc., etc. And yeah, I think I had a few things, but in the interest of time, for those of you who are interested in getting started, there are a bunch of resources available for free in the open source domain that can help you get started. One is VTR, which is entirely open source tool chain that is, can take you from design entry to all the way to developing your own FPGA. There are some examples also here in the link. And Xilinx, major vendors are giving away their design tools for free. You can download them and try it out at your end. In fact, these are, even starting from C, C++, OpenCL can be used. Intel is opening up their entire environment in cloud. This is a free sign up. You can actually sign up on DevCloud and get access to all their tools and actually run them on the servers. So you don't need any physical resources locally. We are not limited by that anymore. So there is enough to explore all in the open source domain to get started. Okay, so I think I've already run out of time. Any questions? Not, thank you. I'll be happy to answer any questions or give you any leads to get you started in this area.
Ma'am, if we create this any processor on the FPGA, still FPGA requires I mean ARM processor or something to tag along because it doesn't have an operating system on it, right? Is it a FPGA standalone?
Yeah, good question. So how can I put an operating system on an FPGA? So like I said, there are many hard blocks available in today's FPGAs. Um, there is a hard physical ARM core that resides on the FPGA, on which you can boot any OS of your choice, and then interface whatever hardware accelerator you would like. So it's completely standalone in that sense. You can also have a soft processor, which you will kind of touch upon in the sessions tomorrow. So there are open source implementations of RISC-V processors that are available that can be mapped onto the configurable logic, and these processors are pretty complete. You can boot OSs on them. So in that sense, you have ways of booting an OS on current day FPGAs.
Yes, ma'am.
Does
And
that
also we require this compiler and all those things also we'll have along with it, right? I mean, that is for sure.
Compiler, you mean for developing custom hardware or for running applications on your processor?
I mean, for running that application on that processor we have built on FPGA, so we require some.
Yeah. All that is like you can if you go by the RISC-V path, all the RISC-V toolchains will be available. Right? You can use the existing GCC based RISC-V toolchain for running applications on the FPGA.
Yes.
Okay. Any other questions? Okay, there is a premium gaming emulator based on FPGAs. I think somebody has shared. That's good. There is a notion of memory slices associated with FPGAs. How does memory hierarchy work in FPGAs, and how does block RAMs differ from conventional DRAMs? Okay, that's a good question. Maybe I missed it entirely. Thanks for bringing it up. FPGAs are entirely SRAM based. Okay, so everything when I say memory on chip in an FPGA is based on SRAMs. SRAMs, as you are aware, they are reprogrammable, but if you power off, you will lose your contents, right? So they are volatile. And you can configure the SRAMs to be whatever you like. If you want it to be simply a scratchpad memory, it will be a scratchpad memory. If you want it to be a cache, it will be a cache, right? It depends on the functionality that you put onto, or how do you configure these SRAMs to function functionality wise. DRAM, no, they are SRAM based. And how do they differ from DRAMs? Yeah, you do not have those kinds of densities as DRAMs as what are available on FPGA, since SRAMs are definitely larger than DRAM, right? There are memory slices. It depends on what you want to implement, right? If you just want an array, then you combine multiple memory elements as an array. If you want it to be, a dual port memory, you configure it that way. They are basically dual ported memories that can be configured in whichever fashion you need. There are some, details of memory hierarchy in FPGAs as well. You have flip-flops, you have lookup tables, and you have dedicated SRAM blocks. In that sense, the timing for each of these blocks may differ. Does that answer your question? Did I miss anything else? All right. Yeah. Okay, so we'll break for now. If there are any questions, please bring them back at 4 p.m. I'll be there, and we'll start the next session on TPUs. Sparsh will be there at 12. All right. Thank you.
Thank you, ma'am.